Now we are going to cover a little bit of a theory. Suppose that we have a system of differential equations, and then the right-hand side of the system can be thought of as a differentiable map from Rn to Rn. So here is an example. If, say, our system of differential equations is, say, x1 prime equals cosine x2 plus x1, and x2 prime is minus x1 plus x2 square, then this right-hand side can be thought of a map from R2 to R2. So in other words, this map takes as input two numbers, and its output is also two numbers. So for example, if, say, I don't know, the two numbers are, say, 0, 1, then the output, the first entry is going to be cosine of x2, so cosine 1 plus 0, cosine 1, and the second entry is going to be minus x1, so minus 0 plus x2 square. X2 is 1, so it's 1 squared, which is also 1, and so on. So you can do it for every combination of the x1 and x2, and overall you have a map from R2 to R2. And so if this map is differentiable, then we can calculate its Jacobian matrix, which is the matrix of first partial derivatives. And then the differentiability is this condition. So informally, we can write it like this. So f evaluated at a point, which is the critical point, plus some small change, is approximately equal to f at the critical point plus the Jacobian matrix times this vector of small change. So let me maybe mention that the Jacobian matrix is the n by n matrix. Y is an n by 1 vector column. F of x0 is again n by 1, and f of x0 plus 1 is also n by 1. When we write it in approximately equals, essentially it means that this is plus something of order y square, which I don't want to go into details of, but there exists a Taylor series, so the next part is going to be involve the Hessian matrix, and then there will be some cubic terms, and so on and so forth. So the rest is complicated, and it doesn't concern us now. So now we just need to understand that the Jacobian matrix is sort of gives us approximation, linear approximation for the map from Rn to Rn in the neighborhood of a critical point. Right? So if now we have our, if we look at our nonlinear autonomous system of differential equations, and then let us make a substitution just like we did in the beginning for linear non-homogeneous systems. Right? So the substitution is x is the critical point plus y. Then the derivative of x is the same as the derivative of y, just as in the beginning. And then when we make this substitution, we get this. So the right-hand side of our equation is approximately the Jacobian matrix times the unknown vector. So remember that f prime of xy is actually a matrix, n by n matrix, and y is an n by 1 vector. And then substituting it back to the system, we get this. The right-hand side of our system is approximately linear. And this linear system is called the linearization of the original nonlinear system. So this is, this is a linear system. It is called a linearization of the non-linear system x prime equals f of x in a neighborhood of the critical point. So it's not just anywhere, but it has to be in the neighborhood of the critical point. Informally, you can say that the linearized system resembles the original nonlinear system close to the critical point, because near the critical point, we have this approximation. But again, I don't want to get into the guts of real analysis here. I don't want to prove these theorems rigorously, although it is possible, but it would probably take another two weeks of something that is very close to real analysis, but I just don't want that. Okay, so furthermore, the critical point is called non-degenerate, of course, if the determinant of if it is a critical point, meaning that the right-hand side of the differential equation is 0, so f of x is 0, but the determinant of the Jacobian matrix is not 0. All right, and here is the theorem that I don't want to prove. So if the linearized system has an asymptotically stable critical point, then the original nonlinear system also has an asymptotically stable critical point. And I suggest that try to figure out whether it is the same thing is true for unstable critical points. Anyway, what it essentially means is, more specifically, if we have a non-degenerate critical point, so now it is important that the critical point is non-degenerate, then we can look at the phase portrait of the linear system and compare it to the phase portrait of the original nonlinear system. And the theorem tells us is if the linear system has a nodal source, then so does the nonlinear system. Same for saddle point, same for nodal sink, same for spiral source, same for spiral sink. So here there is one-to-one correspondence. If the linear system has a certain type of a critical point, then the original nonlinear system has exactly the same type of the critical point. But if the linear system has an improper node, then the nonlinear system may have node or a spiral point, but of the same stability type. So the stability is still preserved. However, if the linear system has a center, then the original nonlinear system may have a center, but it may also have a spiral point, which may be either stable or unstable. We don't know. So essentially, we have like 3 large classes. So here we have one-to-one correspondence. Here we have, well, stability is the same. Type may be different, but the stability is at least the same. And here we don't know, so it is undeterminate. Anyway, in the next part, I'm going to go through a number of examples, so you will see how this